This is E.T. This is really E.T. This is extraterrestrial. This little stone you can see here in my hands is a little meteorite that has arrived here on Earth, and that gives me some knowledge about what is happening beyond Earth, outside, where I'm not always used to think about. My first encounter with E.T. was at the age of 7 or 8. The first time that my parents brought me to the cinema. They got a recommendation from a priest, and I think they never have realized what an impact E.T. could have had on my life. It's pure nostalgia, but you can see it here. Little Elliot, who tried to rescue his E.T. in 1982. And sure, I'm not alone. We are with many amongst us. It's one of the most intriguing questions of humankind. Are we alone in the universe? And sure, you know the answer. At least, I know. I haven't met him yet. But life is more than a 0 or a 1. Life can be about talking about chances. You all know that if you have the possibility to play with money, you have 1 chance out of 2 that the head is on top. And when you can play twice, I hope you still remember the math, it is just 1 on 2 times 1 on 2. So 1 out of 4. So that's the only maths I will tell you about today. Trying to understand what are chances, but chances in a different context. And you can see here, for me in the background, this very famous equation of Drake he has written down in 1961. And what can you read here on this equation? I hope you can see the pointer. But he was after understanding or getting a number upon how many extraterrestrial societies could there be. And as such, he needed to know a little bit of statistics. Statistics dealing with how many stars do we have in the universe, what is the fraction of stars that have planets, and then what is the fraction of these planets that potentially could harbor life. But these 3 factors, I just have shown them now in color, these are the only 3 out there to talk about. Since all the other ones, they deal with biology. They deal with the capacity of a society to build up communication, and in the end, we should count how long that communication could take already. Is it actually true that Drake has written down this equation to give you a number? I say, is it the number 1 or is it 100,000? Maybe, but it's not important. It's not important. The main important thing, and I will come back to that, is that by writing down this equation, he made the implicit assumption that getting life is a convergent process. That whenever you have the possibility, whenever the chemical, dynamical conditions are there, life will be there. But I first need to tell you a little bit about perspectives. I'm used to think about astronomy, and we are dealing with both huge numbers and extremely small numbers. But not all of you are doing that. So today I came here, and the first thing I was doing was I looked at the map, checking for the traffic, and seeing, oh, where can that be? Where should I go? In the Middle Ages, Aristotle was still thinking that the Earth was the middle of the universe, at least the middle of our solar system. And then it takes us up to Copernicus, who realized that it's not the Earth, it's the Sun that is driving us. It's the Sun that is at the center of the solar system. And this is the picture of the solar system we have today, not on scale. We have the Sun, and for those of you who do not know it yet, we have only 8 planets, not 9. We have Mercury, Venus, Earth, and Mars. The first ones are the small ones. They have a solid surface. The other ones, Jupiter, Saturn, Uranus, and Neptune, they are gas giants. Well, some people have seen it already, but I have taken my own little sun with me today. This is my sun, this is this grapefruit, and I cannot balance it, but I put it here. Now, you can't see it then. I'll put it there. If this is my sun today, then I need to experiment a little bit. I need to check here for something very small, and I have it here. Here in my hands, I have pepper. If this is the sun, this is Earth. And then you should realize on that scale, where should I put Earth? Well, I cannot put it here on stage. Well, I can do it, but then you don't have the light anymore. I should need to put it somewhere at a distance of 10 meters. So I'll throw it to you, and you can, I don't think Sophie will have it, but here's Earth. Sophie's Earth, my little Earth, and there I have the sun. And then we should check for Jupiter. This is Jupiter, this is blueberry. If the Earth is with Sophie today, then where should I put Jupiter? What is the proper scale for Jupiter? Well, then Jupiter should be at 50 meters from here. So that's really far in the back. There is Jupiter. And now comes the impossible. This one, this is my nearest neighbor. My nearest neighbor got the name Proxima Centauri. You know why? Proxima Centauri, when I would tell you the distance, it's 4.2 light years. And we put things in light years so that people think it's close by. But 4.2 light years, that's 40 trillion kilometers. So let's think again. Where is my neighbor? You know, we have the sun, we have Sophie with the Earth. Somewhere there, I have Jupiter. Where can I find my neighbor? Well, I cannot do that. But my neighbor is at roughly 2,000 kilometers from here. Let's say in Moscow. So between my sun and Moscow, there's nothing. It's empty. And that's close by. It's my nearest neighbor. And that is where we want to find planets. So that's the challenge. It's not the challenge of 4 light years, it's a challenge of 40 trillion kilometers. So how to do that? First of all, we are lucky. We are lucky in the sense that we are living in a big universe. So a big universe implies luckily also a lot of stars. So how many stars do we have? This is a perspective, so the background you can see, that's an image from the Hubble Space Telescope, and each of these little dots there is a galaxy. A galaxy, for people who do not know that, this is just home of a lot of stars that do interact under the influence of gravity. They live together. And our own galaxy has spiral arms, as you can see it here. And for those of you who do not know it, we live not in the center of the galaxy, we live in the outskirts. And it's good. It's very good not to be in the center of the star. Since there in the center, you have this huge black hole, which is not very pleasant to live close by. And if you live at the outskirts, you don't have many neighbors. Think about society. It might be, and it is, much calmer there. You don't have too many neighbors who are disturbing you. That's true also in space. So, how many stars do we have in one galaxy? Roughly 100 billion. How large is our galaxy? Roughly 100,000 light years. So, I've put a number, 1 and 18 zeros kilometer. Okay? That's already a lot, 100 billion. But then you also have to wonder upon how many of these galaxies we have. Well, sometimes life is simple. We also have roughly 100 billion galaxies. So 100 billion times 100 billion, roughly stars. So that's a 1, 22 zeros. A lot of potential, isn't it? A lot of potential to find planets, to find extraterrestrial life. It is, as Carl Sagan said, the universe is a pretty big place. It is bigger than anything anyone has ever dreamed of before. So if it's just us, seems like an awful waste of space. So let's search for these planets, and you can see it in this title. For centuries, searching of planets is really the synonym to searching for other life. We can see it already when we look to Democritus from Atelier, who lived a few hundred years before Christ. When you look to what he has written down, you can read, if the observed laws of nature are universal, then, since there is life on Earth, life could be present everywhere in the cosmos. Looking to the Middle Ages, we have Bruno, and who said, there are countless suns and countless Earth, all rotating their suns in exactly the same way as the 7 planets of our sun system. For it's utterly unreasonable to suppose that those teeming worlds should be uninhabited. 7 planets. Only 6 were known at that moment. This search of life, this search for other planets, has driven us in North for a long, long time, and we do not stop. Looking to the Pioneer 10 and 11, as some of you will remember, they were launched shortly before I was born. They had these golden plates with them. The goal of these 2 satellites was to go to Jupiter, or the environment between Jupiter and Saturn, to do scientific investigations. But shortly before launch, 3 weeks before launch, Carl Sagan started to lobby and say, you never know that there is an encounter with extraterrestrial life. So we should be prepared, and at least we should tell these people that we are quite often friendly. So they had these golden plates. And you can see our idea on the universe. So you can see here that's a symbol of that we believe in a Big Bang, the symbol of hydrogen, whereas Earth in the solar system, and then the naked man and naked woman. And you can imagine that there was quite a bit of consternation about not them only being naked, but also being the fact that only the man was saying hello. Voyager 1 and 2 in 1977 even went one step further. You can see that the naked man and woman were removed. There was a lot of music on these planes. In more than 55 languages, so also in Dutch, you could listen to greetings. Goodbye, hello, in whatever languages you want. You never know that they would be seen, that they would be found and understood by extraterrestrial life. And from this Voyager, I think one of the most iconic pictures has been taken. What you can see here, for you to the left, but I have encircled it with a blue circle. This little dot here, this one little dot, it's even not 1 pixel in the whole screen. That is Earth. That is Earth taken from a distance of 6 billion kilometers. Small. But as far as we know, that's the only place that what we call human beings have lived their life. So, what makes Earth so special? Is it special at all? Well, it seems that conditions for life seems at least to need an Earth-like planet, and with that I mean a planet that has a solid surface, so not a gas giant. Heat, not too much, not too little. I'll come back to that. Some organic matter and liquid water. That's crucial. And you will hear me saying that back often and often. Why liquid water? Well, that has all to do with chemistry. If you have chemistry, and if you can put it in contact with liquid water, then there are many processes that lead to prebiotic chemistry that are much faster than in an environment without water. So water is a very good catalyst of things that are happening. With one of my PhD students, we have done quantum chemical calculations trying to understand, well, we don't have water, but we have silicates, we have sands. Can we have life? My answer is not no, but my answer is yes, but it takes so much longer. We are missing the catalytic reactions that water can give us in order for sometimes in circumstances which are not always beneficial for life to be created. So how do we then discover exoplanets? Since discovery is only the first step. Well, we are proud that we can use these huge telescopes both on Earth, as here the Very Large Telescope, as missions in space, as you can see here, the Kepler satellites. If I can give you one message, then is it the following. When you go home, you realize that everything you read in the journals, every picture that you see of an exoplanet is arts. It's not science. As of now, we can and we have not yet taken a picture of a planet outside our solar system. But then, how can you then detect exoplanets? A little bit of physics. When you have two bodies, they always interact with each other under the influence of gravity. Even you and I, we interact. I can feel you, but only very, very, very little bit. The reason for that is that we don't weigh enough. But two stars, just to give you a number, our sun weighs 2 times 10 to the 30 kilograms. Two stars do feel each other. And then it's maths, physics. For my bachelor students, you can easily prove the laws of Kepler, that they turn around in elliptical circular orbits around what we call the center of mass. This is when you have two binary stars, the same holes for a sun and its planet. And as you can see in this movie, look very carefully, it's not only Earth that is turning around, but also the sun is wobbling a little bit, since Earth is attracting, is playing with the sun while it goes around. Does it do a lot? No. The sun is moving with a distance of some 500 kilometers. My scales are wrong there, but I cannot put 500 kilometers with possibility for you to see it. So Earth let the sun move. What does Jupiter do? Well, Jupiter can let the sun move with a distance of some 750,000 kilometers. And now you might think, oh, that's a lot. 750,000 kilometers. Put that where our neighbor is, at 40 trillion kilometers. That's nothing. So the method of measuring the movements of planets, measuring the movements of the suns, thanks to the presence of planets, is possible. But it's extremely challenging. So if we are not doing it that way, does there exist another way? Sure. If things are moving, then they have a velocity. The sun is moving thanks to the attraction, the gravity of Jupiter, with a velocity of 12 meters per second. Jupiter is moving with a velocity of 12 kilometers per second. So what are we detecting? We are not detecting these planets directly, or almost never. They are too dim, they do not shine, they only reflect the light of their own sun. Now what we are measuring is the velocity of the host star. And it's just the same as when you have an ambulance that goes from backwards to the front, you can hear the change of the waves, of the sound waves. Well, light is doing that as well. When you have these two bodies turning one around the other, the light is blue shifted, red shifted, blue shifted, red shifted, blue shifted, red shifted. And that's systematics, I can see. So what we do is we detect how host stars, how they move. We call that the Doppler technique. In using that technique, that was a technique that was used in 1995 to detect this first extrasolar planet. A planet outside our solar system, next to a star that resembles our sun. But it came with a big surprise. First of all, what the two people you can see there, Didier Queloz, amongst them, and Michel Maillard, they got a Nobel Prize this year for that discovery. But they didn't expect that discovery, just from the fact that we were wrong. We thought we understood how planets could form. But we had only one benchmark, our own solar system with its 8 or 9 planets. With the rocky ones in the center or close to the sun, and with the gas giants much farther out. But what did they detect? We call it a hot Jupiter. It's a gas giant that lives close to its host star, and where 1 year only take 4 days. So we were not aware, we were even not thinking upon that possibility. So that one detection showed us that our ideas about planet formation were just wrong. Another method to find planets is using the transit method. You can see it here in this little movie. Let's see if I can play it again. Well, that's a bit tough now, since my pointer is not where it should be. Yes. When a planet is moving in front of its sun, the light will dim a little bit. Yeah? How much? Well, I did a little bit of math before coming here, you can compare it with a fruit fly that is flying in front of the headlamps of your car. So this fruit fly is passing by, and a passenger could see potentially that the light is dimmed a little bit. But again, that's not here on Earth. We put the fruit fly and the headlamp at our closest neighbor, at 40 trillion kilometers from here. There is where I should find the fruit fly. Yeah? So that accuracy that we need to detect planets is enormous. But we can do that. And even more, engineers have made us instruments that cannot only detect the transits, but we are even able to study the atmospheres around these exoplanets. Some of these exoplanets we have now detected, and by looking to the light that is passing through these atmospheres, we can tell you, for instance, that a planet has water vapor. That this detection you can see in the back was announced in 2007. For people knowing a little bit on chemistry, we only had 3 points but we knew that that was exactly the band where water vapor can have its absorption bands. And when you have water vapor, you have the potential for liquid water. The nicest way, I think, but also the toughest one, is what we call the direct detections. So the movie that should play and play over again, but doesn't want now, well, that's fine. What you can see are first exoplanets again. What you can see here should be the star, but you can see it has been blanketed by a coronagraph. And 1, 2, 3, 4, these are 4 planets. And people have taken and taken over and over again this data. And you can see how these planets, they nicely follow the laws of Kepler. They nicely have also an elliptical circular orbit around their host star. It's a challenging way of detecting planets, but if you once have seen that, these are the only planets that we see directly. All the other ones, I hope you will remember, are only indirect indications. So what's the status today? Kepler has looked to a lot of stars, and it has looked at one particular region. It's still our neighborhood. It's a few thousand light years from here, some neighbors. The status today is that, I looked it up a few days ago, confirmed exoplanets, we are above 4,000. But how do they look like? This is art. This is the art of exoplanets. Whenever we discuss exoplanets, sure, we do more than just talking to journalists. We think upon what might be their density, what might be their temperature, what might be their climate, what might be their chemical composition. This is the information we use in our models, our exoplanets, hydrodynamical chemical models, and based on the knowledge we have, sure it is limited, we can imagine how a planet can look like. We have blue planets and green planets, we have red ones, we have solid ones, we have gaseous ones, we have water worlds, everything. I guess you have seen these ones as well. As proud Belgian, we were very happy that our colleague Kùzylarsen from Leuven University could announce in 2017 the detection of 7 Earth-like planets, of which 3 of them is in what we call the habitable. So, but what is habitable? I'll tell you about that in a few slides. But first, you know, this was a detection, and it was announced the day I was operated on my knee, so I was full with medals. But okay, I was traveling with all my medal studs, and then I entered the airport, and next to the announcements of Louis Vuitton, the purchase of Louis Vuitton, this was the huge panel, you could just enter the airport, and people were aware that we are doing astrophysics. Isn't it nice? But in all these things, something, when I was preparing this talk, took my attention. I have to admit, I'm not watching movies too often, but now I did a little bit of my homework. And I was surprised to realize how science fiction, even 30 years ago, had ideas about extraterrestrial life in a way that us scientists didn't dare to think. Since here we have Luke Skywalker on Atelier, and you can see there 2 suns, a planet with 2 suns. And now I did a montage. This is Kepler 16b. Kepler 16b is a planet that has 2 suns. It has a circumbinary orbit around 2 suns. And this can be the outcome. Your shadow will never be alone there. Sure, it exists, planets that have 2 mother stars. Since a lot of stars, they do not live alone. A lot of stars, they do have a binary companion. And what about interstellar, where we have the planets of Edmund, Mann, and Miller? Miller's planets, that was the bottom one, you can see there, it was the ocean one, the ocean world. And in the ocean world, that was the one that was circling close to the black hole. So what about Miller's planet? Well, Miller's planet, for people who have seen the Interstellar movie, it had these huge waves. Can it be true? Yes. Since Miller planets was circling very close to a black hole, and you can have then tidal waves, tidal interaction, that gives you the kind of huge waves as we have seen there in this movie of Miller. Man's world. Man's world was an ice world. Is it possible? Yes, it is. Edmund's world was the one which has the closest resemblance to what we know is potentially Mars, and where potentially life could have been. So what is habitable? Habitable does not mean inhabited. Yeah? When people, and then I just say no, when astrophysicists talk about a habitable zone, then a habitable zone is just the zone around the star where you can see it indicated now in green, where the temperatures are not too high and not too low in order to have liquid water. Being too close to your mother target and you have water vapor, being too far away and you have ice. We need liquid water. And indicated now with the arrow, so you have Earth, which is still in the green zone, and you have Venus and Mars just outside it. So just that simple definition, liquid water, was not giving them the possibility for life to be there. But you will agree with me, that might be a too strict definition, but also a too loose definition. Since is temperature the only thing that is driving the formation of life? No, it's not. There are so many more. First of all, you should also realize that this habitable zone, and I indicated here in color bars, it changes depending on the size of your sun. Our sun is a small star, it's a yellow one. Yellow stars, yellow dwarf-like stars. So if you have kids and they make or they draw stars, just tell them that they should have the red color and the blue color as well. Red stars, they exist in many more, they have a huge quantity of red stars than yellow ones. And the blue ones are the most heavy ones, and the more heavy you are, the shorter your lifetime will be. It's never good to weigh too much. So temperature is one of these determining factors, well weighted is as well, but also our place. Since all of the planets that potentially could be habitable, how many do we have out of these 4,000? Roughly 30. But as I was just saying, there are much more conditions. First of all, I come back to that picture, our place in the galaxy. I was telling you, we are quite at the outskirts. It's good. When you have too many neighbors around you, they can disturb the orbits of the planets. You can have collisions. But also, it is important that you are born not too early in the history of the universe. You need other stars that have already died. So in the star that dies, it gives a lot of new chemical elements in the universe. All stars, they are wonderful. All stars, they make carbon, they make nitrogen, they make oxygen. These crucial elements for life to be ever possible. So our universe is roughly 13.8 billion years old. Our sun, 4.5 billion years. So it took some time before our sun was there. That time was needed. This is Earth. What would have happened when our Earth would have been smaller or larger? Bad news. None of them would have had a proper atmosphere. Look to Venus, potentially habitable, But it doesn't have, well, it has an atmosphere and it can hold it. But Mercury, who is even much smaller, cannot hold its own atmosphere. It's again gravity. And when your planet is much bigger, gravity is interacting in that way that your atmosphere is too heavy. So that can be a problem for liquid water. What are other conditions? Well, before that, it's a little bit as Goldilocks, not too big and not too small, not too warm and not too cold. Yeah. But what are other conditions? You see there to the right tectonic plates and volcanoes. Is this important? Yes, people think. Tectonic plates is good to have biodiversity. Volcanoes can give us greenhouse gases. Greenhouse gases, I know we're not thinking positive about that, but we needed it in order to overcome, for instance, the ice ages. We needed the warmth of, for instance, methane, of, for instance, carbon dioxide that can be created that way. And there to the left, you can see that our Earth, its rotation axis is a little bit tilted with respect to its orbit around the Sun. That tilt gives us the seasons. And if you ask biologists, and I'm not at all, they say this is important. It's good to have a slight change in temperature, since it gives you some tension in biology, which as an outcome can give you a much activer biology in the end. I was saying that we have these Earth-like planets and we have the Jupiters. Well, these Jupiters, these gas giants, are important. They are kind of a vacuum cleaners. This little meteorite I have again in my hand, it did arrive here on Earth. And from an isotope analysis, I can even tell you where it came from. If it came from a supernova, if it came from another star, if it came from an all-star. You can tell a lot about the meteorites. Every year we have some 40,000 tons of meteorites arriving here on Earth. But you should be happy that there are only small ones and not the huge ones. And thanks to Jupiter, thanks to its huge mass, Jupiter is collecting a lot of these meteoritic impacts. And as such, it is protecting us from most of the huge impacts that could have damaged life on Earth. Since as far as we know, it is a meteoritic impact that has killed the dinosaurs some 60 million years ago. People are more and more convinced that this is what happened, since this meteoritic impact had an impact and also on the atmospheric conditions, which were not beneficial for dinosaurs. But all of the things I was saying you, it's more dynamics. And that's even not the things I'm doing. These are just my starting points. I know where my planet is, I know what is my host star, so what I am doing. Well, part of our research studies is focusing on climate studies. We try to understand what can be the temperatures, the wind velocities that can be there on Earth. Why do we need the winds? Well, these winds can distribute the heat around the planet. That's only one aspect. And sure, you can be skeptical, since we are basing our knowledge on climate predictions here on Earth, and we know how good we are. Sure, that's a disadvantage, but it's also an advantage, since now I do not have only one Earth, I have 4,000 planets. And so I have the statistics that is in favor of me. I have many more parameters that gives me some way of playing and understanding and going beyond horizons that Earth is giving me. So, what are then the next steps? If I can tell you something upon temperatures, wind velocities, and so on. How to find ET? Is it an idea to go to our neighbor there in Moscow? At only 4 light years from here? That's always a question I'm getting from the journalists. Well, sure it's not. Since with the current technologies, it would take me roughly some 100,000 years. Yeah? That's why some people in the Breakthrough Starshot project, amongst whom we have Zuckerberg, they're working on a kind of an idea where they try to make kind of a satellite, potentially not larger than a stamp, and that can fly with a fraction of the speed of light. But this will only be, or that is only an idea, to go to our nearest neighbor and maybe take a picture. So you will not be on that satellite. Captain Spock was still thinking that in order to know if a planet, if it was possible to go to a planet and not to be poisoned, he should go there with his Enterprise and check manually if an atmosphere is poisonous. Well, he's proven wrong. We do not have to go there to know that. What we do is, we will, and we are currently doing that, taking, as for instance the other spectrum we have seen already, we take spectra, we call it, of these exoplanets, and we are analyzing the spectra to tell you what is the chemical compositions of these atmospheres. And so when do I then talk about signatures of life? Since not everything, not every signal in the spectrum is a signature of life. Well, now it comes to chemistry. When do we talk about biosignatures? Well, I will give you a very simple example. We all know that cows are generating a lot of methane. Okay? So, would the detection of methane be an indication of life on a planet? No, it's not. Since methane is only one fingerprint. What is happening with methane in the atmosphere, and you see there the chemical reactions, we have chemical reactions starting from ozone, making oxygen, we have water reacting, and in the end, you see here the last row, that methane will be broken up and will become CH3. So spontaneously, methane does not like to live together with ozone or with oxygen, since it is exactly ozone and oxygen that are the incentives for methane to be broken up. Well, then the idea is, if you have a detection of methane and oxygen, or why not H2O, ozone or carbon dioxide, you have several fingerprints of which you know that under normal circumstances they do not like to live together, but the fact that you see them implies that one of them has been just generated. You can compare it with when you go to a student's apartment and you see 3 students there having pizza, then you know the pizza has just arrived, since knowing how fast students can eat pizza, the pizza is just delivered. The same holds there. When I find methane and ozone, I know that methane has just been delivered. So there is a huge influx of methane. So this is what we are aiming after. Understanding what is a biosignature and see what are false positives. Trying to get a grip on that, since that's the tricky part. I'm living in a very lucky era where I have very brilliant colleagues that make us instruments to really look for these biosignatures. And you see here on the slides various amounts of new instruments that are just launched or will be launched in the near future. Well, near for an astrophysicist means within the first 15 years. Yeah? I'm very proud that, for instance, at our institute, we are not only working with Plato, but also with the James Webb Space Telescope that will be launched hopefully in 2021, and the Ariel mission for 2028, where we will look for these atmospheres around Earth-like planets, really. It's so amazing that people know how to make these instruments. Well, for students who are looking for a job, we have currently 18 new positions in the field of exoplanet sciences. 18 PhD positions with the idea upon what are biosignatures, what can I trust, what are the challenges in the fields. One project is called Escher, the other one Chameleon. And so what are the challenges? I should tell you a little bit about that. First of all, I was just telling you that so for you now, your sun would be to the left. When the light of your sun is traveling through the atmosphere of the planet, we have a signal of the planets. One of the things which is complicating our studies so much is if planets have clouds. If planets have clouds, the clouds, especially when you look in the infrared, they dim, let's say, the spectrum. You do not have this very deep absorption and emission lens anymore, but you get a very flat spectrum, yielding it impossible for you to know what is beneath it. Luckily, clouds are mainly affecting us when we are doing studies in the infrared. We are better off when we combine both information from the infrared with optical measurements. But even there, it is a challenge. Since, for instance, what you can see here in the spectrum in the back is if we do simulations, for instance, when you have an ocean surface, so that's the blue line, when you have conifer forest, that's the green one, and when you have a halophyte surface, that's the purple one, you see that from far they look very much different, especially in the strength of the bands. But you see that each of these surfaces do have similar absorption bands at particular wavelength regions. This is mainly caused by water also being important. So let's assume this to happen with a little bit of cloud coverage, and you can see where is a challenge. But now I'm talking about the cloud coverage, I even cannot tell you how clouds are formed. What is the composition of cloud formation? This is what we are currently studying. How can we form clouds, and how will these clouds look like? I start to miss more and more the upper part of my screen, but for people of you who are curious, when you look at the upper part and you go back to the bottom part, you have the whole slide. So, cloud formation, how does it work? So what we are doing is with my PhDs and postdocs, some of them are working in quantum chemistry, we're trying to understand how these little molecules, how they can form larger gas phase cluster, and at some point you get a transition towards a dust species, towards a solid state species. And you would think, well, we know that. We know how it works here on Earth. But sure, it's happening different there. Since I have another chemical composition, I have another soup of chemical elements, so also there the clouds will be different. I need to understand, not only for the sake of looking to this data, but also since when clouds are forming, they are taking up part of your gaseous elements. I give you an example. When you would have clouds forming of carbon dioxide, we all know carbon dioxide and the greenhouse effect. Well, when part of your carbon dioxide is now in your clouds, so solid state, you have less carbon dioxide that is left, and so it impacts my temperature calculations. We do not have a lot of help from industry, since industry is mainly cars, so carbon dust, but I'm not interested in carbon dust. I want to know what is happening with titanium monoxide and silicon monoxide and things like that. These are the constituents I have to study now in order to understand how cloud formation can happen on exoplanets. And that's only one step, since now we go to the next step of that chemistry. If I just give you a soup of simple chemical elements, simple I mean you have some atoms and molecules with 1, 2, 3 atoms to make a molecule. RNA and DNA are much more complex. And I want to understand how we can have the formation of RNA and DNA. And so the first step I need to know is, how can that formation happen? Not under an Earth-like condition, but under a condition that can be vastly different. What happens, for instance, if my sun is not a yellow star, but is a very dim red-like dwarf? If I have, let's say, the dark ages versus the light ages. Light means you have a lot of photons. Photons, they can easily break up some of the molecules. This have a huge impact. If molecules can break up, you have a new set of chemistry that can start. Completely different to the dark ages. But I do not have the chemical reaction rates for my dark ages. I don't have them. People were not interested. So we need to start either experiments or quantum chemical calculations to get the potential energy surfaces in order to try to understand what might be chemical reaction rates. This is one of the topics of the Asia project. And then we go further. RNA and DNA, when you look to the macromolecules, they have a very specific sequence that is repeated over and over and over again. So how do simple, naked molecules know that at some point it could be good or beneficial or whatever, in order not to be very randomized, but to have a sequence of its own? I have some macromolecule, and then it's attached to itself, and you have it again and again. You get a sequence that comes back and back. How? We don't know. We don't know how a regular structure can be imprinted in order to have this sequential macromolecules. One of the ideas we have is that the interaction of a molecule with a solid state surface can do the job. Since a solid state surface, look at the stones I had, look at my little meteorite, it has a regular structure. So potentially, that regular structure can be implanted on the molecule, on the macromolecules, and it can take that as an example, as a kind of catalyst, in order for it to rebuild itself and itself again, and getting a kind of a self-assembly. We don't know. We're trying to, or we will, in the next few years. This is one of the pathways we will study. But as you will all realize, I have given you already a few ideas, a few of the parameters we are dealing with stars and chemistry and dynamics, and there are so many. I'm not anymore talking about models that we run on a laptop. I'm talking about models that we run on supercomputers, since especially the chemistry is the limiting time step in all of my calculations. So we have these huge jobs running in order to get things as good as possible based on the knowledge that we have. But this will not be the way that I will analyze any new data that will arrive. Since when I'm giving you one spectrum and then I have to go to my supercomputer and I have to calculate for years, then we won't proceed fast. So what we are doing now is, I will have two people now that will use, as you know, the idea of artificial intelligence in order to, what we have now already on templates, learning computers with you using these classical deep learning processes, how can other environments look like without us having to do the calculations over and over and over again. And that kind of algorithm can help, hopefully, and it will help us, and when we get the data, and at least do a job in scanning this huge parameter space and tell me, this parameter space, that corner might explain your data, but also that one, and potentially another solution as well. So some final thoughts. I've started with this thought already. Is life convergent or is it contingent? I don't know. Drake's equation, as I told you, the underlying idea of Drake's equation is that if life has a potential to form, it will. There is a sequence, it's a determining step. In 2000, Zwart and Bromley has given another idea. They are supporting the idea that life is contingent. Just look to that picture there. If you can imagine that each of the conditions I was already a little bit explaining you about, and we can discuss on that for hours, that each of these conditions is, for instance, one chance out of thousands that you're successful. And the next one is also one out of thousands, and the next one as well. Then, although I do start with a sample of 10 to the power 22 stars, you realize that you do not have to take too many steps in order to have a fraction smaller than 1. Nobody yet can tell us if it is the upper row or the bottom one that is happening. What is biology, Sophie? You should be able to tell us. But, as often, everyone takes the limits of his, her own vision for the limits of the world. We have started with Aristotle and his own visions. And then people in the Middle Ages have to go beyond their horizons. And we came to Copernicus. And now we are living in a world with many exoplanets, with many stars, a huge amount of stars, with maybe even many universes, a multiverse. So it seems like man is almost nothing anymore. Who are we in a universe that is that huge, in a universe that is maybe even not alone? From one extreme to the other one, especially early 2000s. From a philosophical point of view, there have been a counter idea, the anthropic principle. Carter said, although our situation is not necessarily central, it is inevitably privileged to some extent. That idea has many versions of it being written. You have the weak and you have the strong anthropic principle. While I'm saying this, is that I think this is correct. We are not necessarily central, but we are privileged. But we often do not see that. And we often do think, some of us do realize that they are privileged, but then they do think that they are more privileged than other people around them. I like what Ronald Reagan has said in 2000 during his speech for the United Nations General Assembly. Perhaps we need some outside universal threat to make us recognize this common bond. I occasionally think how quickly our differences worldwide would vanish if we were facing an alien threat from outside this world. So, here are we, human beings. Are we the strength, or are we the limiting factor in our search for extraterrestrial life? I think we are both. We are both the strengths, since we try to go beyond Earth. But we are also the limiting factor, since how difficult it is for us to think upon all our knowledge, all our equations, but in a sense all equations which are all written by humans. How can we get that human being out of the equation? How can we think upon something that is potentially not imaginable for us? Potentially it is just us who are the limiting factor in finding, understanding, getting in contact with extraterrestrial life. And with this last slide, coming back to this iconic picture taken by the Voyager on initiative of Carl Sagan. A picture which expresses a philosophical view on us,
human beings, coming into being thanks to astronomical reflections on the nature of our biophilic universe. Quoting the words of Carl Sagan, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives." Thank you.
Danser sur la corniche du Belvédère. On va danser sur la corniche du Belvédère. On va danser sur la corniche du Belvédère.